this Poynting vector, and it is this term. By definition, it's the three of them. 1 over mu naught E cross B. So you want to, when you assemble charges, and you want to know how much energy leaves that field, you got to take the magnitudes of those, of the electric field and the magnetic field, cross them, divide them by 1 over mu naught. Now, why is that important? That actually says then, if you take charges and assemble them, or move currents around, and anything just moving charge itself, you're creating energy is leaving that system. And if energy leaves a system, what is that creating? Our electromagnetic wave. This energy leaving a system is the energy of that electromagnetic wave that's created. Like on that little lab simulation I had you do, the charge was moving up and down. Well, the work it took to move that charge up and down, the amount of electric field you had to initially move it, it's going to decrease a little bit. So there's still less energy in that system now. They keep adding it there, of course, to keep it oscillating. But some of that energy leaves that system. What is that energy that leaves that system? That's the radiating radio waves that go out from a big antenna. This is shown based on just how much work it takes to assemble charges and keep a current going against a back EMF. To keep current still moving. And applying what we previously knew. The Lorentz force law, looking at work over time, and then just trying to understand what this is. By understanding this, you had to put that, so it's the work per unit time, per unit volume. And from that, you get this rate of, you go back and get this again. So the work per unit time, the energy as a function of time. So for a radiated wave, the energy as a function of time is going to be equal to, at the moment, what the electric and the magnetic field vectors were, their amplitudes and those amplitudes only. That is that energy leaving the system is the electromagnetic wave itself. And the Poynting vector tells you the rate that energy is leaving the system. Or, if it's sunlight on your skin, it's how much energy is absorbed by it. Could be absorbed by your system. How much, the maximum amount you could absorb. Poynting vector. Now they do an example in the book. They basically say from this, and they developed a, let me use this term. This is known, this Poynting vector here, this S, is energy flux. Because energy flux is how much energy flows into something over an area. It's the energy flux density. The energy flux density. And later on, they show within a couple equations, you can take this and get a continuity equation for energy. Energy into a system equals energy out of it. But I'm not going to really focus on that. Example 8.1. Look at that one. That's just a simple cross product. And for a wire, I like that problem, by the way. Hint, hint. Poynting vector, rate that energy goes through an area, goes through a surface as it leaves the volume. And that volume just could be the whole surface area of a cube, the whole surface area of a sphere, whatever the volume shape is. Poynting vector, rate of the energy flows out of a system due to moving charges. It's how antennas work. It's why they work. It's why moving charge, you can't have an antenna without charge moving up and down. Why? Because that charge moving up and down creates that electromagnetic wave. Okay? Maybe I should have done this earlier. Sorry if I confused you without it. But I did want to backfill today. Hope this made a little bit of sense. Thanks.